Here is the phase noise with 3 dBm into the amplifier, and I have also at the same time here, this is the Wenzel oscillator when I measure it directly. And it's interesting to see that at wide separations, here above about 50 Hertz, my filter amplifier has much less phase noise, but at very close range it adds noise, and a significant amount of noise up here. So this is the Wenzel oscillator, and this is my filter amplifier. And why it is adding noise at very close range, I don't know. I look at 10 Hertz offset, that is like this, and it's here, that is minus 140. That's not very encouraging. I have tried different input powers here by setting different attenuators settings, and as it turns out, lower power makes the noise a little lower. But then I tried to reduce the current by increasing this resistor from 16 ohms. 27 ohms seems to be the optimum, and then I don't have to reduce the power from plus 3 dBm. The best I have seen was with 3 dBm input and 27 ohms for the source resistor. And that gave, at 10 Hertz, here, minus 143 dBm. Or maybe minus 142. I didn't have the patience to wait more than 6 hours for this test. When I run the unit as an oscillator in the circuitry like this, and then feedback, the noise is a trifle lower as compared to when I run it as an amplifier at the same power level. That is something I cannot explain, but I observed that also earlier. Here is the phase noise plot from the previous video, nerds69, and at 10 Hertz here I observed minus 144. Although the straight line through the other points comes more like minus 143 here. So the accuracy isn't too high because there is noise in the measurement. Here is what I've seen as an oscillator after 17 hours, and then at 10 Hertz I come here, that is minus 143. So I see as an oscillator minus 143, but as an amplifier minus 142. And both those values are not at all what I expect. It's pretty clear that I have noise originating in the amplifier, so I have turned the filter the other way around to feed the Wenzel into the eye impedance side through 4.7 pf. And then on the output I have a transformer stepping up the voltage by a factor of 2. And then I'm measuring here with my signal analyzer, the 2-channel receiver. That is accurately 50 ohms. It means that the crystal is looking into now 12.5 ohms. And that's pretty close to what I had. I had 10 ohms in this previous measurements. I have been waiting for 15 hours now, and what I see is like this. at 10 Hertz here, the level is maybe something like minus 147. The statistics is not good at all enough here, because the red points, that is the imaginary part, is almost equal to the yellow point, which is the real part, and which is positive, except for a few places where there are maybe spurs, or maybe the signal to noise ratio is so low that it's just negative for reasons of random. I have saved an old measurement of the vent cell, which I have here, and the scale is the same, and also the horizontal scale, very close to the same, and at wide separations it's obvious that the new measurement here is much better. And at 10 Hertz here is 10 Hertz. This is the filter now without an amplifier, and this is the vent cell oscillator. So it is clear that the filter is now improving over the vent cell. So what I see is what I have seen before is obviously noise in the amplifier, so I need a better design to amplify for this crystal. This is to verify the use of the FETs as a low input impedance amplifier by sending the signal into the sources of 3 parallel transistors. I have not matched the output, I just load the drain by 50 ohms. This will be okay at the close range, but it will not give a good performance at wide frequency separations. But this is just to verify that things look good at close range. This has been running now for 10 hours, and what I see is the following. 10 Hertz here, something like this. That is minus 148, and the noise is lower because the imaginary part, the red you see here, is at the same level as the yellow, which is the real part, and is positive most of the points, but there are occasionally blue, means negative values. That is probably just due to noise. So this looks okay. At a maximum input power, where I see some heating of the crystal, the voltage here on the source is 80 millivolts peak to peak. Then on the output impedance is in the order of 500 ohms. On a 500 ohm resistor, if I place it here, I can see 2 volts peak to peak. And that means I have 1 milliwatt on 500 ohms. And the noise floor will be the noise figure of the amplifier I put here, plus the room temperature noise of the 500 ohm resistor, or resistance of the FET. The FET will have no gain at large frequency separations, because the impedance on the source will be very high compared to the 10 ohms impedance of the input impedance of the FET arrangement. So gain is going to be 0, because the impedance here is higher than the 500 ohms on this side. But the limit I will get is noise figure minus 174 dBc per hertz. That's usually called B0. And if you look at the specification of my vent cell oscillator, it says at 10 kilohertz 166. So that is a typical limit, that order of level. Correction, noise figure minus 174. That is amplitude noise plus phase noise. So if I assume noise figure of 2 dB, B0 could approach minus 175 dBc per hertz. Now I want to do a little bit better than that, and to that end I can use an amplifier here with noiseless feedback. That would reflect the impedance of the crystal to the other side, so I could use the varying impedance to make the noise lower away from the resonance. I have measured by use of interferometry the noise of various amplifiers. So I have one with this BUK 75150 with noiseless feedback, but I have another one with 5 parallel J310, and the noise is different at different power levels. At plus 13 dBm, it's the black curve. At plus 10 dBm, it is much better. So probably at 0 dBm it would be still a little better. This is what the 5 times J310 amplifier looks like. It has air-wound coils on the input and on the output, and that is a little bit unsatisfactory for this purpose, because the coupling between the windings isn't perfect at all. There is a lot of leak inductance, and that makes the mirroring of output to input less perfect. Here is the input impedance when the unit is terminated in 50 ohms. So it is 42 ohms and minus 4 ohms reactive, and the span is 5 megahertz here. This is the output impedance with 50 ohms on the input. And here is the output impedance with an open input, and it's strongly reactive, as you can see. But it is not very resistive, it's far from the center at 50 ohms. And here is the output impedance with the input shorted, and it's on the opposite side and fairly good distance away from the 50 ohm center. I placed a capacitor in series with the output and an inductor in parallel with the input, and now I have a 50 ohm input impedance with this dummy, which is accurately 50 ohms. And then I see something like 150 ohms. And now the input is open, just that inductor is in place. And then I see a high impedance. If I tune out the reactive part marker and select the appropriate frequency like that, it looks like about 3 kilo ohms. And here is the shorted input, and it is something like 30 ohms. So from 30 ohms to 3 kilo ohms, that's a factor of 100. And I think by using ferrite cores I could make this ratio bigger, but there is a risk that ferrite cores add noise, and I have to look at that before deciding what to do here. To investigate ferrite cores, I'm using this setup. First, a signal source. That is the Wenzel low noise oscillator at plus 13 dBm. Then an amplifier with some JFETs in it, followed by an amplitude limiter with crossed N4148 diodes, and then two 6 dB amplifiers, and after that a low bandpass filter at 10 MHz, and then an attenuator so I can reduce the signal level and see whether that is important or not. And after the signal source I have an interferometer. That's a hybrid and a stepped attenuator into another hybrid. And then a second chain where I can step the phase by various lengths coaxial cables, and then a fine tuning on the phase and a fine tuning on the amplitude. This is done with capacitors, variable capacitors, because resistors that are variable are dangerous. And then the position for the device under test. And then the hybrid. And when these are set for the amplitude and phase to be identical here, there will be zero output in this point, and the sum of the two signals into this resistor. And then to analyze what comes out here, I split the signal in a hybrid, and then there is a stepped attenuator, and on this side there is a coupler so I can see what is going in this leg, and then a stepped attenuator, and then the two-channel direct conversion receiver, followed by the computer running Linrod. And this minus 9 dB coupler is followed by a hybrid that splits the signal into two equal parts. One goes through an amplifier to the oscilloscope, the other goes directly into another channel of the oscilloscope. And I use the oscilloscope to see the level of the signal that goes through here, because I want to not adjust the interferometer for zero. I want it to get a signal at a specified amplitude. Means I want to suppress the carrier by maybe 40 decibels, which means I would suppress the noise, sideband noise from the signal source as well as that carrier by 40 dB, while the noise of the device under test will come at its full amplitude. So this way I should be able to see sideband noise at levels I couldn't see directly. The devices I'm going to test is first just nothing, just a straight connector, female to female. And the next is a noisy 2 dB attenuator that I happen to have, plus that female to female. And then finally the interesting thing is two ferrite cores with 1-to-1 windings, which will let the signal through with a low attenuation, and I can inject a DC current from a DC source through 100 ohms and a very big capacitor, two 47,000 microfarads in parallel, because I don't want to inject any noisy DC current, because that would modulate the signal. So this is the correct diagram. I can inject a DC current this way. So there will be the same DC bias in both iron cores, because they could become noisy when the ferrite is biased to some extent. There is also a 20 dB coupler here at the full power level, and that is used to trigger the oscilloscope. Makes it easier to see things, to have an always phase correct display. As a first test, I break up one of the legs of the interferometer. Means I do a quite normal measurement of the sideband noise of the signal that comes out from the signal source, and use that to measure device number 1, means nothing, and device number 2, that noisy attenuator. This way I will get a number for the noise of that attenuator to use to compare with what it will show in the interferometer later on. Here is the amplitude noise of device under test number 1, and I have saved this to use later. And here is the phase noise also, and here is phase noise only, and you can see the phase noise is reliable up to about this point. And I waited 45 minutes, and I don't think phase noise is interesting in the very close range. The noise of the attenuator will be probably pure amplitude noise. So the interesting thing is this curve. And this has very good statistics all the way down to 5 Hertz or something. I have introduced 10 dB attenuation here, and then reduced the attenuation by 10 dB here and here to keep the level into the direct conversion receiver the same, means close to saturation of the AD converter in the sound card. Here is the amplitude noise at the 10 dB lower signal level, and here is the saved result from before, and the scale, as you can see, is the same. So something generates something like 4 or 5 decibels of noise. No, not quite. Maybe 3 dB at 60 Hertz, all the way up to 150 or so. This indicates that something from this attenuator up to these attenuators is producing AM noise that depends on the signal level. It could be hybrids, and so there is this hybrid and this hybrid, and of course these things, but not this one, because this is made by coaxial cables and they're not making any noise. Here is the phase noise now at the 10 dB lower power, and the previous, the saved at the full power here, is very similar. So the effect of adding that chain of various things is to introduce some AM noise, but not phase noise. To try to find where the noise comes from, I have connected from this attenuator output, which is set to 0, a cable directly to this hybrid on the input of the 2-channel receiver. And that eliminates all the possible noise sources in the interferometer. And here is what I see. This is the full power, and it is plus 3 dB because it's not split by the hybrid. And the previous result, this is what I have now with the full power and without going through any of the components of the interferometer. And here is the result I had before at full power. And you can see there was some noise source, because now it is much better than before. So I will connect to other parts and move the cable until I find which component is producing noise. I have connected a cable here and then inserted the signal into this point. Okay. And here, yes, okay. And here, no problem. And as it turned out, the 20 dB coupler is inserted here and not here as I showed before. But it's okay also to send the signal in here, but not here. There is a problem with this hybrid, which is just a rat race of coaxial cables. That doesn't seem possible. Well, until I open it and find I have forgotten to solder in one of the connectors. So there is just the copper put into the BNC and no soldering. So I will fix this and I hope this will help. I have soldered that connector and now the hybrid is even more noisy. Here is the reference when I inject the signal at the other points further down the hybrid, further down the interferometer. So it's clearly more noisy now. Soldering the cables did not help. Surprising. Now I'm using this hybrid instead. And the noise is no longer present. Here is without the interferometer, and here is with that hybrid replacing the one made from cables. So here is the result with that other hybrid, and I'm running the device under test 1, this thing, and I will now insert device number 2 in series. It has an interesting behavior. It starts with some wide noise that gradually gets narrower. And if I look here, this is what you see. The sidebands, that's because I introduced vibration. This is on the table now. If I knock on the table like this, so that is something I have to avoid. So I will leave this running for a little while and then start evaluation. I can reset, and here is what it looks like now. 1 hour later, I have collected correlation spectra for 5 minutes. And what I had 1 hour ago was like this. So I take this as the stable value and save it. I have reduced the power into the device under test by 10 decibels. And this is what it looks like. And it has been running for 24 minutes, so the statistics is very good. Here is the result I had during only 7 minutes at full power. And somewhat surprising, I find that the sideband noise is the same at these two power levels. I have reconnected the other leg of the interferometer, and this is now attenuator number 2, this is number 1, and I have made a table. So with infinite attenuation I have these numbers. with the AM noise at different frequency separations, and these readings on the oscilloscope. With the other leg also in line and with the attenuation set to 1.9 dB, I read now 44 millivolts. That is 20 decibels below what I had without the second leg. Means I have reduced the carrier by 20 decibels, a factor of 10 in amplitude. And now I am looking at what comes out on the noise measurement. Here is the continuous phase shifter, and here is the oscilloscope. It is now channel 1 where I have 1 volts, a little bit more than that, but you can see that I have a minimum here when turning the phase shifter. It means the carrier is in phase between the two, or rather the carrier in the two legs is exactly in the opposite phase because I have a minimum at this phase relation. And the Linrad screen shows a lot of noise now. What you see here is when I turned the knob on the capacitor for the phase adjustment. So I have reset and I wait for a more stable or a less noisy line here. It will take just another minute or so. It has been running for 40 seconds now. I can read at, for example, 50 Hertz, like that. And there I see minus 131. Here is AM noise and phase noise. And the phase noise is much lower and is of course very sensitive to the phase angle I set by adjusting for the minimum here. So this phase noise is of no interest. The sideband noise I can measure now, minus 131, is about 20 decibels worse than what I saw before with only one leg of the interferometer. The carrier is reduced by about 20 dB, but the noise is not reduced. So this is as expected. I have improved the sensitivity for measuring sideband noise by 20 decibels now. I have changed the attenuator now to 2.6 dB and adjusted the phase and fine-tuned also the amplitude. So I have a 10 times lower level in channel 1 of the oscilloscope. Channel 2 is too low to measure with a reasonable accuracy, but I have reduced the carrier another 20 dB, so the carrier is now 40 decibels weaker than without the second leg of the interferometer. And here is the amplitude noise, very strong indeed. I can look again at 50 Hertz and I read something like minus 111. And that is indicated as a 20 decibels worse value compared to before. So this seems to be okay as a method of measuring low levels of added sideband noise in passive components. I think I forgot to mention that before I had a hybrid here, but now I need that hybrid to replace the one with cables in it, so I put the 6 dB coupler instead to get two different gain settings for the oscilloscope. One with the signal going through and through the amplifier for channel 1, and the other minus 6 dB and into channel 2. Because the dynamic range of the oscilloscope isn't big enough for the voltage differences I'm looking at. Or rather, the output voltage of this amplifier is limited. I have connected now device number 3, and this is with only one of the legs in the interferometer to establish the attenuation through this unit, which means to find the voltage on the oscilloscope channel 2. This is after 15 minutes, and actually when I compare with device number 1, means nothing, there is a small difference. Looks like about 2 decibels at 25 Hertz. But I don't want to wait for the statistics of this because I have the tool to use the interferometer. Already by reducing the carrier by 20 dB, I see the noise of the pair of ferrite cores very clearly. This is what I see now, and here is what I should have seen if they didn't add any noise. So this is pretty obvious that they are noisy, but I will check now that also with device number 1 I don't see this kind of increased noise. Now I have the device number 1, means nothing in the interferometer, and the carrier is suppressed by 20 dB, and this is what I see. And this compares to the measurement without carrier suppression, which is like this. So the difference from here to here is noise from the interferometer itself with no noisy object extra added in it. There is a problem here. I have just touched this BNC connector, moved it a little bit like that. And there is a noise source of some kind. Well, suddenly it is gone. So I have to clean connectors and look carefully what could be the cause of this. I have cleaned this one now, this one, with isopropylic alcohol. And now I move it like that. And it shows a more or less normal sensitivity to that. It is fairly strong movements. And I test the other one. And I will have to clean that one also. So now I cleaned it and I move it a little. And it looks more normal now. Now I am again measuring this device number 3. And on the screen, this is what I have after 4 minutes. And then as a saved image, here is what I had with device number 1. Means only the interferometer. And the difference is too small. It means all the noise I was seeing was from the connector. This is an old box I have had for some different purpose, and there were surplus connectors in it. I probably never cleaned them. So one has to be careful with this kind of experiments. To really know whether the ferrites are okay or not, I need a better interferometer. But I will try first whether this device number 1 was okay. It was an old one with silver center conductor. Here is another one with gold center pins. I am now running with this other variant of dot number 1, and this is what I have, and previously this is what I had. So there is no difference. This is the limit of what I can do at this time. This is the phase adjustment box. It has 4 switches and some cables in it, each one half the length of the previous one. And this is what I use to set the coarse phase adjustment. I have operated all of the switches 25 times now. And the device under test is just nothing, just a female to female adapter. And now what I see on the screen is this. What I saw with the same experiment previously was this. So operating the switches has improved my interferometer dramatically. I have operated all the switches 50 more times, and this is what I had before with 25 operations, and this is 75. There seems to be a small improvement. Now things go fairly slow, so I will suppress the carrier another 20 dB. Now again, device number 1 means interferometer only at 40 decibels carrier suppression. And this is what the screen looks like. This is amplitude noise. And here is phase noise also. And as you can see, the phase noise is lower than what is indicated by the measurement, because the imaginary part is equally big as the real part. The interferometer is now good enough for the purpose. This is the latest measurement I made with the device number 1. I wanted to establish whether I can use ferrite transformers or not, and that is in an oscillator, and the absolutely best I can hope for is this red line here. That is the B3, and then the flat noise floor, I don't think below minus 190 is possible. So that means the critical frequency is here, and the interferometer that I measured just now are these crosses. So if the ferrite core contributes significantly amounts of noise at 100 Hertz, I should be able to see that. And if I don't see it, it is certainly good enough, and then I can use the ferrite cores. Now I'm looking at device number 3, the 2 ferrite cores at 40 decibels suppressed carrier. That's 135 millivolts on channel 1. And then this is what I see. And if I look at the phase noise also, you can see the phase noise is significantly lower. And actually it's the phase noise I'm interested in, so this looks good. And here I can see that this is really the noise from the device. To what extent it is partly AM noise, I don't know. That depends on how carefully I have adjusted the phase. But it's enough to know that it is significantly lower than the AM noise. Device number 3, running at minus 40 on the amplitude, increases the noise of the interferometer itself by less than 3 dB, 2 dB, 2 dB, and here 3 dB. But it means that the transformer pair adds less than the noise of the interferometer itself, or at similar levels. So this is fine, and as long as there is no bias current, the transformers are good enough with some margin, because there are two of them and they contribute equally much, both of them. I am now sending 100 milliamps of DC current through the ferrite transformers. Interesting enough, the AM noise is now a little bit lower. Here is what I had without the DC bias, and here is the DC bias. And the difference is about 2 dB. It means all the AM noise is gone, more or less. But when I look at the phase noise also, I find that the phase noise is not very different from the AM noise anymore. So the phase noise has increased, while the AM noise has gone down. Or maybe the difference is smaller just because the AM noise is lower, because I don't remember exactly. I found the phase noise insignificant previously. I will increase the current and see what happens. This is 200 milliamps through the transformers. The amplitude noise is still lower than without the DC bias. Here's what I had without DC bias, and here is what I now. I'm not so sure what happens down here. Maybe I have introduced some vibrations. Anyway, the phase noise here is now the same as the amplitude noise at close range, and close to at 100 Hertz, and it seems that the phase noise for the 100 Hertz spur has split into two components now. I don't know what that could mean. Anyway, it seems quite a lot of current can be sent through these ferrites without causing serious noise problems. These currents, of course, change the entanglements. If I switch off the power supply, you can see the difference. Now, this is a very small difference because I have a 40 dB suppression of the carrier. This is 400 milliamps. Noise is still very low. I mean, AM noise. What I had without any current is this, and it's significantly higher. I have to check that. Maybe I made a mistake. I could have had vibrations or some problems during this measurement. Anyway, this is 400 milliamps, and I look at the phase noise. Phase noise and AM noise. Phase noise is significantly higher than the AM noise here, so I have to verify that that is really so, because it is significantly higher than the imaginary part. It's strong enough to be visible also without correlation. So this is no good. And now there is no BC bias. And this is the old measurement without any DC current through the transformers. So there is a small difference. Something was not quite right in the previous measurement, but differences are small enough for me to not worry about it. I'm happy with this result, and I will use the ferrite transformers for the noiseless feedback amplifier to put right after the crystal. There are 11 turns bifilar on the ferrite transformers, and with 100 milliamps it would be 1 ampere turn. that is no problem. Maybe even 2 ampere turns, but not more. Could be the design target for the noiseless feedback amplifiers.